and I started the recording. Okay, so let's talk a bit about this code evaluation. So I already mentioned what the point of this is. So the point is that so when we are doing elaboration, then so one main job to do is to do conversion checking or unification. So for conversion checking, we need an evaluation which is actually a complete evaluation with respect to definitional equality. So if I want to decide the convertibility of two values, then I have to completely evaluate everything. So this is kind of we need a complete evaluation. But for quoting, so the problem is that when we are doing evaluation, we get values, but values are not really so they cannot be stored or they cannot be manipulated. And the reason is that we are in values, we are using either closures or we are using kind of higher order abstract syntax, and higher order abstract syntax are just functions in Haskell. So this is not storable or serial, cannot be serialized. And closures can be stored, but they have a very large amount of implicit sharing. So there is a size explosion. So if I want to serialize some value which contains closures, and the problem is that there is lots of sharing, but the sharing is not really observable. And if I unfold every closure, then the problem is that the closures can contain closures which can also contain closures and so on, because every closure captures the current environment, but then the current environment can also contain more closures. So there is
can you remind me, why do you need serialization?
Because I have to, so when I'm doing elaboration, I have to save some kind of interface file. So I take some source file, and I'm doing elaboration. I have to save some module file or some interface file. It's of course it's not very efficient if the only thing that I can type check an entire project is by re-elaborating everything. So I do not want to re-elaborate everything. I have to store the result of elaboration.
I see.
Okay, so in values we have closures or we have higher order abstract syntax. And so there is a size explosion. So for example, I can do some quick example. Like if I have some local scope and I have an f equals something, g equals something, h equals something, and then I return something like an f of g of h of blah blah blah. Or maybe have some lambda expression here, and then what happens is that g. So if there is any binder inside g, then it captures f. If there is any binder inside h, then it captures f and g. And of course, if this h captures g, then there is a reference to g in the h's capture, but there is also reference to f in g's capture. However, there is also reference to f in h's capture. So you can see that when we are always capturing the environment, there is this significant amount of sharing, but the sharing is not really observable. And in principle, there are ways to solve this. So in principle, we could do some way of converting the unobservable sharing into observable sharing. And there are some ways in Haskell to do this. For example, we could try to use the mechanism which is available in compact regions. So there is a way to say that we want to copy every value into some compact region, but we want to copy it with sharing, and that would do some kind of so this allows us to serialize values even if there is some sharing involved without losing that sharing. But it's a bit inconvenient because although we can do a serialization, we cannot do like the usual transformations, or we cannot just walk value and exactly know what is shared and what is not shared. So I'm sure there are other ways of recovering this sharing, but of course they all have some overhead, and they are not the most convenient thing to do. So instead, what we do is that we have an evaluator, and the evaluator can do complete evaluation, and complete evaluation means that every beta redex is reduced. So all beta reductions, all unfoldings. But when we want to do a quoting, then we instead do kind of an incomplete evaluation. So we perform all beta reductions, but not all unfoldings. And the reason is that we want to avoid this size explosion. And then the question is, so what kind of unfoldings do we want to avoid? So which unfoldings to avoid? And actually, this depends on how we handle the meta variables. To be more precise, it depends on meta variable scoping. So let's look at an example. So like the first version is when we have top level meta variables. But the top level meta variables are, let's just assume that we have the kind of meta variables which we solved last time, which is kind of a typed and dependency ordered meta solutions. Okay, but I mean, just to give some preliminary intuition, so why is the handling of meta variables the critical thing here, or the and the reason is that so elaboration, in the elaboration output, so if you want to serialize or store or save or manipulate or do anything with the elaboration output, we already have the syntax which is coming from the source file. So we already have elaborated syntax coming from source file. So if you have a source file which does not contain anything which has to be inferred or filled, then we already have the complete syntax for the elaboration output. So if there are no holes, no inferable things, then we already have the complete elab output as a piece of core syntax. However, when we have holes or implicit args, then we have to generate. So we have to generate coarse syntax, kind of from nothing, of course, not literally from nothing, because so these holes are inferable from all kinds of type dependencies, which are already implicit in the available part of the core syntax. So we have to generate core syntax, and the way we generate core syntax is by quoting. Right? Because like all of these operations, so conversion checking, scope checking, occurs checking, this partial renaming operation, so all the computationally expensive operations, they all involve values. So we are always working with values, so all of the expensive operations work with values. But then we have to go back to syntax, and the way that we can go back to syntax is by quoting. So this is the only place where we get pieces of syntax which come from quoting. So this is actually the only way to have size blow up in elab output is by quoting. Is by getting meta solutions from quoting. Okay, so this is the only way to have a size blow up. So if you want to avoid size blow up, then the way to do it is to do a smarter way of quoting. But then, so I mentioned that the way to avoid size blow up is to avoid unfolding. So avoid some unfoldings. But what? So the kind of unfoldings which can be avoided depends on how metas are scoped. So depends on how metas are scoped. So okay, now let's look at an example with top-level metas. So if I have top-level metas, then it already gives me some opportunity for avoiding unfolding, because I can say that there is like question mark 0, and there is question mark 1, and there is question mark 2, and so on. And then we have a bunch of metas. And then we have the actual module which we are elaborating, or the actual expression. So if you have this kind of setup, then we want to avoid some unfoldings in meta solutions, and the only unfoldings which can be avoided are the meta solutions themselves. So in this case, only meta solution unfoldings can be avoided. Why? Because we have this kind of scoping. So we know about the scope of a particular meta variable. So we know that this 2 can depend on 1 and 0. So this solution is still well scoped if I have an expression here which refers to 0 or to 1. But it is not well scoped if I want this to refer to n, for example. And it is not well scoped. It is also not well scoped if I want this meta solution to refer to any later definition, which comes from the source file. So metas can only refer to other metas in scope. But actually this is already pretty helpful. So if you have this kind of setup, and we say that we are only avoiding meta solution unfoldings, then it already helps. But it is okay, so let's just edit this a bit. So this is the simplest version. And there is a bit more sophisticated version. So a bit more sophisticated version is when we have so metas have arbitrary top level scope. And now it is possible to have like a block of meta variables here, and then we can have a foo which comes from the source, and then we can just continue defining new metas, and then we can have a bar, and then we can have another meta block, and so on. So essentially the way to implement this is to say that there is a potential block of meta definitions between every two definition which between every so it's interleaved in this kind of way. Okay, and now it is possible to avoid unfolding. We can avoid unfolding meta solutions plus source definitions in scope. And this is the version which I am currently using in the setoid TT. It's also the version which I implemented in small TT previously. And this is pretty good because I mean usually the programs are not very deep, so we have lots of definitions on the top level, but we don't have nearly as many local definitions. And the local definitions.
Can you highlight this source definition in scope stuff between the two examples? I don't really see what it is referring to and what is different in the second example compared to the first one.
So I'm marking meta solutions with question mark. So question mark number are meta solutions, and otherwise it's a normal definition. So this has a normal identifier for a name, and this is a question mark number, and these are the meta solutions.
Yes, and in the first case, how it was different?
So in the first case, the difference is that I have to have every meta solution in the topmost level. So
and you don't know which one is going to foo and which one is going to bar. This is the problem.
No. So here I have just one block of meta definitions, which is the topmost thing in the entire module, and below I cannot put any meta solution, for example here. So there is this separation. So we are separating the elaboration output into two halves, and the first part is all the meta solutions, and the second part is all the source definitions.
And do you need to refer to the source definitions in some metas? Is that what we want?
I don't need to refer to. Actually, I don't need to refer to anything because I can always unfold all definitions in meta solutions, but then they are in normal form, or I mean not necessarily normal form, but they are fully unfolded, which causes a size explosion.
Yes.
So here, if I have this setup, then I have to unfold every reference to source definitions because source definitions are not in scope at this point. So I have to inline them.
Okay, I think I see that now.
And
so in the second case, you can keep some of the source definition. You can keep more of them folded, right?
Right.
Okay.
Right. So here I see that between any two source definition, I may have a block of meta solutions, and then it is possible. So So this solution can refer to foo. And if I have, so this solution can refer to foo and all the previous meta solutions. And here, if I have a question mark 6, then this solution can refer to bar and foo and all the previous stuff. So the general phenomenon is that if I have more precision in metascoping, that means that I can have a smaller elaboration output. And kind of the logical endpoint of this is when I say that meta solutions can appear in any scope. So this meta solutions anywhere. And if I have a meta solution anywhere, then I can do something like, for example, I can have maybe a function, and the function has some type. We can also look at some concrete examples. So maybe the function is this identity function. Okay, but let's make this implicit. And maybe I say that I want to define this foo as this ID. And then how is this going to work? Let's just. So if this is ID, then the elaboration output will look like this. So I get an A, which is the type. And here I have an ID of A, and here I have an ID of A arrow A. Okay, we can actually continue this a bit. So this is a classic example of exponential science elaboration output in Hindley-Milner inference. And you can see that I can continue these IDs and it's going to double. So the implicit argument will be double the size whenever I'm adding a new ID to this application. And this is parenthesized in this way, right? Because function application is parenthesized to the left. So it looks like this. So I have an ID at a higher type applied to ID at a lower type, and then it's applied to ID at an even lower function type. Okay, and this is okay. So let's write down the source expression and then different elaboration outputs depending on what kind of solution we are using for metascoping. So if we have a source expression which looks like just ID. So this is the source. This is output 1. So output 1 is essentially completely unfolded meta solutions. In this case, we don't even have in this case, we have no block of meta solutions whatsoever. So maybe I should also mention it. So this is the simplest version, which uses some kind of glued evaluation, which does this avoidance of unfolding. But there is an even simpler version, and the even simpler version is where we don't even have this block of meta solutions. We just inline every meta solution right into the source definitions. And that's quite obviously that's the worst solution, because then everything is just completely unfolded. Okay, so this is kind of the worst solution, and we may have top-level metas, and the top-level metas produce exactly the same solution as the kind of the top-scoped metas, because now we do not have any So we do not have any kind of dependency of meta solutions on any top level definition. So here we assume that we already have an ID, but these meta solutions, they don't really depend on ID. So these two versions produce the same elaboration output, and it's going to be, so we have 1, 2, we have 3 methods. So we have 0, which is lambda a.a, right? And we have 1, which is lambda a dot 0a, arrow 0a, and then we have 2, which is lambda a dot 1a, arrow 1a, and then we have full aa equals lambda a dot, and then we have this idea expression, but we don't unfold the meta solutions. So here we have 0 applied to a, here we have 1 applied to a, and here we have 2 applied to a. Maybe I can get rid of these parents. Let's not get rid of them. Okay, so we can already see that if we continue this ID, then it's going to be a linear sized. But if we are continuing this ID, then it's going to be exponential sized. And what about full local metascoping? If we have full local metascoping, then it's not an asymptotic improvement in this case, but it's kind of still a cosmetic improvement and some constant factor improvement. Okay, because in this case we say that all of these meta solutions are pushed under the binder. And then we don't have to introduce this additional abstraction on the local variable. So in this case we can just completely skip this lambda because A is already in scope. So if we have the meta solutions in some local scope, then we do not have to abstract over this local variable, we can just simply refer to it. Okay, and then we just return the same expression, but now we do not have to apply these meta variables to A. And so this full local metascoping, so it would have more effect if we also had some local LED definition. So if I have some LED full, but inside the LED full I have some LED bar, and then LED dot, and then I return something. Then I get more opportunity to have sharing in the elaboration output, because now I can put a meta solution here, like a let question mark 0, and then the 0 can refer to bar. So this is the most powerful version of this idea. Okay. So now I have, so here what I have is a file which is kind of primitive. So this Haskell file only implements kind of so we do not even have elaboration or meta variables or anything like that. So this is just untyped lambda calculus. With a distinction of top-level definitions and local definitions. So this is pretty simple, but it is already possible to demonstrate this avoidance of top-level unfolding. So we can illustrate avoiding top-level definitions. And in general, so no matter what solution we use here, if we are only talking about evaluation, then this is all we need. So if you want to do an evaluation which has some possibility of avoiding unfoldings, then I think it is enough that we say that the environment is split into two parts. So it's enough for all solutions above to split into some prefix and some suffix. And the prefix is not unfolded, and the suffix is always unfolded. Of course, there are some use cases for having a more fine-grained control over unfolding. So if I'm working in a proof assistant, then it also makes sense that I want to very specifically toggle the unfolding for certain definitions. So interactively, I say that I want to have fine-grained control. But if I'm only doing elaboration, then I think it is completely sufficient to just split the environment into an unfoldable and a not unfoldable part. And that's what we have here. So we have terms, and then we have local variables, and we have top-level variables. And we have applications, and lets, and lambdas. And then we have spines in values, and so the value is either a lambda or a local spine, a local variable applied to a spine, or a top-level variable applied to a spine. But here we have this trick. And the trick is that we have this extra lazy value here. So what is this extra lazy value? So the way this works is that this top name spine 1, so if I have a top x sp and then I have some lazy value, what this represents is that the x sp part is kind of the result if I don't unfold x. Because this is this top refers to a defined thing on the top level. So if I want to do full normalization, then this particular constructor would not even be necessary. So if I always unfold a top level definition, then there is no need to have this kind of spines, because I can always just unfold x. But here I want to avoid unfolding in some cases. So this XSP is the result of evaluation if I don't unfold x. So if x is not unfolded, then x may be applied to some particular spine. But this is kind of stuck because x is not unfolded. So I cannot apply the spine to the value of the unfolding. So this is the result if I don't unfold. And this is the result if I unfold x. And this makes it possible to choose between two results. And so I can do a traversal on values, and I can choose to look at this, and then I get something which does not perform this unfolding. Or I can force this lazy value, and then the computation is performed which is triggered by the unfolding of this. But if I don't look at this value because it is lazy, then I don't have to trigger all that kind of computation. Okay, so, and I have a top level environment and I have a local environment. And now I have two kind of environment for output to input to evaluation. And this local evaluation is completely straightforward like before. But when I have a top definition evaluation, I am creating a VTop. So I'm creating a VTop and I apply X to the empty spine. And here I perform this lookup. It's a bit inefficient to create this thunk merely for performing a lookup. So if I am doing a high performance implementation, I arrange that this lookup happens immediately. So this lookup happens strictly because I don't want to create a thunk just for performing an environment lookup. But here I don't really care about performance. Okay, so application is kind of the same here, and evaluation of let. So this is a local let, it's also the same, and lambda is also the same as before. However, application is not the same because application has to handle the VTop. So I have this extra case. So if I have a VTop and I want to apply it to some U, then I have to actually perform application on both possible results. And that's why it looks a bit like a non-deterministic evaluator. And I think it would be a good name to call this non-deterministic evaluation, but it's much longer than the old name, which is glued evaluation. So I think there is merit to just calling it glued evaluation as before, because it's so much shorter to say that. Okay, so here we have to perform application on both kind of possible results. So, and here, because I just have to extend the spine with an additional argument, it is really cheap to immediately perform this computation. So it makes no sense to delay this computation because it's just creating a new SAP constructor. So it's very, very fast. It would be a lot slower to create a thunk just for doing this. But here, so this application can be arbitrarily expensive. And that's why we are creating a thunk here. And in general, when we have this kind of non-deterministic unfolding values, then every eliminator has to have some action. So all eliminators have action on these non-deterministic unfolding values. So if I only have an untyped lambda calculus, then application is the only elimination which I have. It's kind of the negative, like a projection-like elimination for functions. So I have to implement the action of application on VTop. But if I have like sigma types or inductive types or whatever, or other kind of computation rules, then I have to extend every such elimination with an action on VTop. Okay, and we have fresh name handling as before, and then I have a quoting operation, but now the quoting operation is a bit smarter because it gets an additional argument which is called unfold top, and if this is true, then we are unfolding top level definitions, and if this is false, then we are not unfolding top level definitions. And otherwise it's pretty much the same. So So here I'm just quoting a spine, and if I'm quoting a value, then so if I have a top, then if unfolding is true, then I just continue quoting this t. So this is kind of the fully evaluated choice, or the fully unfolded value choice. So in this case, I just continue quoting with this t, and otherwise I'm just quoting the spine, and I'm keeping the top level reference as it is. And I'm just checking if this is correct. So if we have x here, and we have this fetch, then we are quoting. Okay, it seems correct. Yeah. Okay, but we also have an evaluation function for the top level program. So the top level program is just a sequence of top level let definition. So it's kind of a pair of a name and a tm, and then here I'm just doing a fold over all of this and evaluating them. So I'm evaluating everything in the empty local environment, but then I always extend the top level environment with a new definition. Okay, and here I have so I have an unfolding option, and I have a top level block, and I also have a term which is under the top level block. So what I'm evaluating here, evaluating top level block plus a term in this or the term under that block. And let's see if this example actually works. So I have some top level block, which is, as usual, church encoded natural number defined up to 100. And I have a term, and then the term is, so the term has a local definition. So it has a let, which is a local definition, which is this foo. And then I want to multiply foo with foo. So what is this? So this is SZ and SSSZ. So this is the church number, church numeral 3. Right? So if I want to multiply 3 with 3, then it would be 9. But now I have a choice, and I can do an nf top of true of top and tm, and then I get 9. Yeah, so I have an s, and it seems to be okay. And if I do an nf top of false top tm, then I get a mul. So here I have a mul, and this is 3, and this other is also 3. Okay, so this is kind of a very small demonstration of this evaluation, but I think we can also talk about conversion checking and kind of approximate conversion checking. Probably I can just try to do some small implementation of this conversion checking. But first, let's talk about the idea. So the idea is that if I have a choice between unfolding and not unfolding, so this extra choice, results in like lots of freedom. So now we have a significant amount of freedom how to implement conversion checking. We have extra opportunities in implementing unification and conversion checking. Okay, and now we have like a bunch of different strategies. We have different strategies, and there are many ways to combine the different strategies. So for example, there is a strategy 1, and the strategy 1 is just to do conversion checking with full unfolding. Okay, but this is kind of as usual, so we already had this previously. And conversion checking with full unfolding has a big advantage, and the advantage is that it's a complete decision algorithm. So if conversion checking says no, then two terms are definitely not convertible, and if it says yes, then they are definitely convertible. So this is a complete decision algorithm, and actually this is in many situations this is the only possible complete conversion checking algorithm. So this does the job, but this can perform a lot of unnecessary work because it normalizes and unfolds everything. In many cases, we can give an answer without performing all of that kind of computation. So in many cases, we can have an approximate conversion checking, and then the approximate conversion checking is not complete, but so it can return three kind of results. So the approximate conversion checking can return a definite yes or a definite no, or it can also return a maybe. And if it returns a maybe, then we have to fall back to some complete decision algorithm. But there are many different ways of implementing this approximation and this fallback. Okay, so we have this, which can be very expensive, but which is complete. And then we have conversion checking with no unfolding. And this is the fastest, but it's incomplete. Right? And if we have these, then we can already do a very simple combination of these two. So we can have the third kind, which is what I'm doing right now in setoid type theory, but I will also talk about different versions. So this is a kind of a single choice between 1 and 2. So what does this mean? So this means that we start doing conversion checking, and if we hit a VTOP case, sorry, yeah. So if we hit 2 VTOP, and then we have some x sp v, and then some x prime sp prime v prime, then what we do is that we try to use 2 on x prime sp. So we try to do a conversion checking on this spine without unfolding anything. And if it fails, then we just continue with 1. Okay, and otherwise, so if we have a VTOP of something, v prime, or if we have v and then a VTOP of v prime, then we just continue with the 3 algorithm of v prime. So I believe that this is the simplest combination of 1 and 2. So we start the conversion checking, and if we hit this kind of VTOP, then we try to do the approximate conversion checking, and if it fails, then we continue with this kind of complete decision algorithm.
And what is the relative speed up of the second version with respect to the first? Can you give some rough estimate?
It's arbitrary. So it can be really arbitrarily expensive to do 1 versus 2, because I mean, so we are working in some kind of strong general type theoretic language, and so the speed up is only bounded by the strength of the type theory. So
okay, let me put it another way. Is there some complexity estimate based on something, number of lambda functions, number of arguments, something that would be that, okay.
No, there is no, so there is no complexity. So there is no way to combinatorially characterize the complexity of functions definable in a usual type theory. Because
okay, so is it just some practical rule of thumb that the second version gives improvement? Significant improvement?
Yes.
Okay, then my question is, why we are only switching to the second version in this VTOP case?
Because otherwise the distinction is irrelevant. So the distinction between 1 and 2 is only relevant if we have VTOP. So if I'm unifying two closed values, and by closed now I mean that they do not refer to any top level definition. So if I unify values which do not refer to top defs, then the distinction is irrelevant between 1 and 2. So then 1 and 2 becomes exactly the same thing, and 3 actually never encounters any VTOP. So 3 just becomes the same as 1 or 2. So if we don't have top level definitions, then 1 is the same as 2, which is the same as 3, right? And yeah, so this choice is only relevant if we are hitting a top. Because if you are hitting a top, then it could look like I have some top level definition, like I have a full, then so this is kind of a top, then locally I can have some conversion checking of T and U, so conversion of T and U, and it is possible, for example, that T is just lambda x dot or lambda fx dot maybe fxx, and likewise maybe U is the same, but there is an additional beta rex. Okay, so these two values are convertible, but here I have an additional beta rex because I have this identity function application here. And in this case, if I'm doing 1, then it's the same as 2, because there is no unfolding anywhere, and 3 is also just the same. But if I have a conv of maybe foo or some lambda fx dot foo fxx, and here I have a lambda fx dot foo f. Let's also have some y here, so we have a foo of fxy, and then here we have a foo of fxx. So now this situation is that I have a reference to foo on both sides here, so conversion checking just goes under all of these lambdas, but I also have to have a y here. So conversion checking goes under the lambda, and then we have to do conversion checking of these two expressions. And depending on the definition of foo, this can succeed or fail. So if foo is defined in a way such that it doesn't matter that we have xy here and we have xx here, then convergent checking succeeds. But if here we are only doing a convergent checking with no unfolding, then it's going to fail. So we can try to kind of step through what this tree does here. So what this tree does is that first we go under all of the lambdas, and then we hit the foo, and then we try to unify the spines without unfolding. But then that fails. So here we get a failure, and then we fall back to 1, and then it can succeed or fail. But the point is that so what is the main point?
So sometimes the method getter can return a result that is not maybe, and we are fine with that because that is the same that would be found by method 1. And then we have short-circuited the unfolding, right?
Right.
Okay.
Right. So I believe that the very important benefit or the important advantage of 3 is that we only do this kind of backtracking at most once. So backtrack at most once, which means that by doing this kind of approximate fiddling or this approximate checking, we cannot really do much worse than just by using 1 all the time. So
okay, so again, if we start with method 2, right?
Yeah.
And we are going deeper into the tree, and at any point that we fail, we switch to method 1 and go deeper with method 1 until the end, right?
No. So if you are doing 2, then so this 2 is just it's immediately. Okay, let's write out what this 2 does. So if we have a vtop xsp and then we have a vtop x prime sp prime, then this algorithm just continues with unifying these things, and otherwise it just fails. And in this case, so if I have a vtop on one side and something else on the other side, then it fails. And likewise, if I have it here. So a convergent checking algorithm which performs no unfolding. So if I get a vtop, then it still has a chance, right? Because I don't necessarily have to do an unfolding. I can just try to unify the spines. But if I have a vtop on one side and a non-vtop on the other side, then because this algorithm is not allowed to unfold anything, then it can only fail. And there is no backtracking involved anywhere. So this is just really the simplest version of saying that we are doing a convergent checking, but we are not allowed to look at this and this at any point.
That's right. So is there, my question is there any point where we are switching back from method 1 to method 2?
No.
Okay,
the only
that's what I'm asking.
So method 1 is just what it says in the here. So method 1 does not switch from anything to anything. It's just a complete convergent checking algorithm.
So it is the same that I was saying, that the first time you hit something where method 2 fails that needs unfolding, you start unfolding everything from that point on, going deeper.
Yeah, but this choice, it only happens in algorithm 3. So this, you can imagine that these 1, 2, 3 are functions such that 1 and 2, they are only calling themselves recursively, and 3 can call itself, and it can also call 1 and 2. Okay. So these are all different functions, and all of these functions make sense just by them So this 1 and 2, they make some sense by themselves, and this is a function which can do a call to 2 or 1. And this is the only function which can make a choice between different unfolding strategies. And these cannot make any choice. Okay, and so what I started to talk about is that because this is kind of a single choice between 1 and 2, an advantage is that we cannot make an asymptotic screw up. So we cannot ruin performance asymptotically compared to just using 1. Okay, maybe this is kind of a hand-wavy statement, but intuitively, if we are only trying to do this approximate checking once, then okay, I mean, in general, it is also possible that we have a very large term which computes to a very small term, right? So it is still possible. So this is not actually true that we cannot do an asymptotic screw-up, but it is not usually the case. So usually the case is that the unfolded terms are much smaller than unfolded terms. Or the normal forms of unfolded terms. It is possible that I have a very large term which computes to a very small term, and it is also possible that actually performing the computation using some evaluation strategy like using lazy evaluation, I can very quickly compute a very small term from a very large term. So it is possible to quickly compute a small term from a large term. For example, there are kind of obvious examples. Is that I have a constant function like lambda xy x, and then I apply this to maybe like lambda xx, and here like I have some huge church numeral. And if I'm doing a core binding evaluation, then this can be very large, but evaluation can be still very fast because every huge numeral is just okay. I mean, if this starts with a lambda and then I have some huge string, because an evaluation of this is immediately returning a closure, then this immediately computes to some very small thing, even though the term itself is very large. But this is the exception. Okay, so we have the assumption that unfolding increases the sizes of things. And this is usually true. And if this is the assumption, then this algorithm does an approximate checking only once and then immediately falls back to the complete decision algorithm. Okay, but what if we don't do this? So for example, what if we say that we have like a naive or kind of a nested backtracking approximation. And this is actually used in some places in Agda and Coq as well. And I think it's not a good idea, but let's look at this. So here, the way it works is that if we have a v top x spv and v top x spv, then try to use So how should... Right. So try for x sp and x prime sp prime as for v prime. And all of the other cases are kind of standard. Okay, so this nested backtracking approximation is actually, it only calls itself. So it only calls itself. It doesn't call 1, 2, or 3 recursively. And the way it works is that whenever we hit the top, then we try to unify the spines, and if it fails, then we try to unify with the same algorithm the results of the unfoldings. And this is basically, this can backtrack an arbitrary number of times. And I think that this is probably not a good idea. And the reason that this is not a good idea is because it's kind of an eternal optimist algorithm, because it says that, for example, like, I already tried to do this approximate checking like 100 times and it failed 100 times out of 100 times, but this next time when I see this additional spine of v top, then I will also try to do this approximation, and probably, or maybe, it works this time. So this is kind of an eternal optimist, because it always tries to do unification or conversion checking without unfolding. But in practice, it is possible that so in practice, it is possible that that the convertible values are like very far away in terms of computation and unfolding. For example, if I'm doing like a computation with a left fold on a list, so if I have this kind of accumulator like recursion, then usually what happens is that, like a folder in Haskell, it just updates the accumulator, and then we only get the actual result at the very end of this recursive chain of calls. So we have to compute all the way down using this accumulator recursion, and we only get some result which is probably convertible or possibly convertible to some other result if we are performing like all of this computation all the way down. But if we are using something like a folder, then it is possible that maybe we can compute something, and then there is a chance that we already see after some prefix of the list that the two expressions are the same, even though we are not performing every unfolding. But this is just kind of a very hand-wavy example. But in general, if we are using folder, then it's much less likely that we get an approximate solution before having to compute everything all the way down in this case. And so the question is, so how far away are convertible values? So if convertible values are very close, then this for kind of algorithm is probably really good. because then it makes sense to just try to avoid unfolding as much as possible. Okay, but what if convertible values are far? Then 4 is actually really terrible, because we are just doing approximate checks over and over and over and over and over, and probably we are having like a large asymptotic slowdown because we are just doing this completely futile approximate checks all the time. So approximate checks are kind of futile, and we should just compute as quickly as possible. Okay, and it's my impression is that in real life what usually happens, or what happens in practice. So in practice, what happens is that we can get like a large gains by trying approximation in a limited bounded way. However, in some cases there is some real heavy computation involved. Like we have two numbers, and the numbers are different. The numbers are different, and the way that we are computing the two numbers is like two completely different chain of function calls, and it's never going to be. So at any intermediate point of evaluation, we are never going to get anything which is convertible in an approximate way. So in practice, I think what happens is that we can get large gains by trying a limited approximation, but if approximation fails, then just go as fast as possible. Yeah, like in real world, it can happen that like we have a lots of shorthands and type definitions, or definitions which are used like type synonyms. So for example, IAGDA, I'm doing some abbreviation, like I'm abbreviating sigma type with another definition, or whatever, and in those cases, it is very likely that all that we need is just to unfold some relatively small number of shorthands. So like unfolding small number of kind of definitional shorthands is pretty common in CoCAGDA. But when we really want to perform heavy computation, then which we shouldn't do this approximation anymore, we just do heavy computation efficiently. Okay, and I believe that Coq and Agda both does 4 in some way. I'm not sure exactly in how way, but I know that Coq and Agda both does this 4, this very nested backchecking, and I think that it's contributing to some very heavy slowdowns in convergent checking benchmarks when we really do a convergent checking, like large church encoded numerals or large data structures or stuff like that. Okay, and so what is another version which I thought about? So I think that this 3 is okay, but there should be a way to make this a bit more flexible, because
so do I see it right that in the actual code it is really just small differences, those that you have highlighted? So it actually, once you have implemented 1, it is just a little bit of tweaking of going for 2, 3, or 4.
Yeah. So the only difference is, so if I have some core language and I do a convergent checking, these are the only 3 lines that have to be changed.
So it's much like about guessing the statistics of the input and getting the branch case probabilities right when to choose which one.
Right, right. But I think it's so. This is a good choice because here, if we are wrong about the guesses, then we are still not in a much worse place than when we only using this one, right? Because here we are just adding some extra approximate checking cost, but then we are not adding any iterated extra costs. So we are only doing backtracking once. So yeah, so it's not significantly slower even if our guesses are completely wrong about unfolding. But if we do this, then this is going to be horribly slow if our guesses are wrong about unfoldings. Okay, but I think it's a good idea to make this a bit more flexible. So this 5 variant is extend. So we say that it's like 3, but with a certainly fixed amount of backtrackings, fixed number of backtracking, like backtracking, so we get some number of shots at backtracking. So this 3 is kind of, it only gets one shot at backtracking, but maybe we can also do like 2 or 3 or something like this. So this 5 would be like if we have a veto x SPV and then a veto x prime SP prime V prime. Okay, I think I forgot what is the good way to implement this. So maybe okay, I think I remember. So I just say that there is an extra argument to 5. So there is an extra int arg to 5, and maybe let's call it maybe, I don't know, n. So when we do this, then if n is not 0, then we do the same thing as in 3. Okay, not exactly the same thing, because what we okay, there are a bunch of different versions. So there are a bunch of different ways of limiting the number of backtracking, because one possibility is to say that if I have a non-zero n, then I can continue with using 5 n minus 1. Right, so I can try to unify these spines, right? So I can try to unify these spines, but inside the spine I have one less opportunity of doing a backtracking. And if it fails, I just continue with a complete thing. And also, if I'm doing an x SP and I'm doing an x prime SP prime, sorry, so if I have like this, then this also counts as consuming one unfolding. So yeah, I can say that this is also 5n minus 1 v prime, etc. But this is just one possibility. It is also possible to say that this does not count as an extra unfolding, or maybe that if this fails, then we still want to continue with not with 1 but with 5. So there are like a bunch of different versions, and At one point I thought about this, but I kind of forgot about it. But yeah, so there are some ways to parameterize this tree algorithm to give it more chance at unfolding before completely reverting back to full conversion checking. Okay. Okay, now the question is, so what should I talk about? So what I could do here is to just implement these 1, 2, and 3 algorithms in this file, for example, and it's not very hard. So I could do that, or I could also talk about like what kind of changes do we have to do if we are using GLUE evaluation in elaboration. So here I am only talking about conversion checking, right? And yeah, so which one should I do? So should I just write an implementation for this 1, 2, 3 now? Or should I instead talk more about what else should change if I'm using this GLUE evaluation?
Yeah, I would prefer the elaboration.
Okay. Raphael is a very decisive person, so we have to follow Raphael's wishes. Okay, so let's talk about like what happens in elaboration. Elaboration plus GLUE eval. But before we go to elaboration, actually we can go to unification, because I only mentioned conversion checking here, but I can only there are already some changes in unification, and then there is a big change depending on whether we allow local methods or not. So big change. So local methods versus top methods only, but there are some common changes. So for example, one common change which we have to implement is that if you are doing approximate unification and not only approximate conversion. So the difference between unification and conversion is that unification sometimes it has to do meta solutions. And it's pretty important that if you are doing an approximate unification, then it's very similar, but so it's very similar, but now we have to be careful because we only want to solve methods. So we can only solve methods if actually the unification problem cannot be removed by any full computation. So if the unification problem is rigid. Okay, so what do I mean? So example, so if I do a foo of so let's assume that foo is a top level definition, and I want to unify foo (0) with maybe foo (1), right? And if I'm doing the approximate unification, then all that happens is that I have to unify (0) with (1). Because if I'm not unfolding foo, then I only have to unify the spines, so I have to unify these two methods. However, it is it's not a unique solution, so it is potentially a non-unique solution if I'm doing this, right? Because it is possible that for example, foo is a constant function, and if foo is a constant function, then there is a way to unify the two sides without having to solve 0 or 1. And in general, if we make a meta solution which is not really needed, then it means that we are overly restricting the meta context. So now maybe this solution rules out kind of other possible solutions. And this is something that we want to avoid. And here I can mention that Coq just doesn't care. So if Coq does this approximate unification, Coq is completely happy to do these solutions, even though it is not necessarily a unique solution. So Coq doesn't care, but Agda does care. So if Agda does an approximate unification, and then in the approximate unification mode it has to solve something, then Agda just backtracks. So it counts it as a failure. Okay, and so if you do unification, then we can still use this scheme of 1, 2, 3 kind of functions. So we say that one can solve metas, right? Because whenever we are doing conversion checking with full unfolding, then we are not doing any. So we are only solving unification problems which must be solvable in order for two terms to be converted. So this can solve metas, and the conversion checking with no unfolding cannot solve metas. And interestingly, the 3 can also solve metas. So why is this the case? So we always start unification by calling 3, right? And if you look at the definition of 3, so if this 3 does not hit this case, so if the 3 function does not hit the approximation case, then it just simply continues, and every choice that it makes is completely like rigid. Because if we have a top on one side and something which is not top on the other side, then the only way that this can ever be unified is by performing an unfolding. So here we don't lose any possible solutions. And if we consider like the usual cases, so when we have a lambda on one side and a lambda on the other side, then we just go under the binder, and then there are also no loss solutions here. And the same when we try to unify like a neutral, like a rigid neutral. So the only way that we can lose solution is here we go into a spine, but it is possible that all the work that we are doing inside the spine unification can be completely unnecessary. And that's fine. We can also solve meta variables when we are in 3 mode. Okay, so this is unification. And Okay, but I mentioned that there is a difference between local metas and top level metas. And the difference is in renaming. So there is the pattern unification. And so what did we have previously? So previously, and let's just put this into some big comment block. Okay, so previously, what was the pattern unification? So pattern unification looked like this. So if we have a meta, let's call it alpha, and it's applied to some spine, and then we want to solve it with RHS, and then we are working in some gamma. And we also know that alpha is actually it's a closed thing, and it has this kind of telescope type. Okay, so this is kind of non-scoped methods. So this was the situation, and then we can solve this if actually this spine is so this is solvable if this spine is a renaming, which is also an epimorphism. I mean, in categorical terms, it's a renaming which is an epimorphism. But if we are just looking at the renaming, then it means that this is a list of variables such that each variable occurs at post once. So it's kind of a unique list of variables. And we also know that this RHS can be strengthened. So this RHS only depends on the variables which occur in the spine. And we also know that RHS does not depend on alpha. Right, so if we have these three conditions, then there is a general or there is a unique solution to this. The unique solution is that we say that alpha is defined to be a lambda of spine dot, and then we have to perform some kind of renaming on RHS. Okay, so this is previously, and okay, and what happens if we have top scope methods? But the last time I already mentioned this. So the last time I already mentioned this, that if we have top scope methods, then we have to do a strengthening in the meta, even in the meta context. Because now we don't just say that this meta variable is just in some kind of empty, is floating in empty space, but rather what we have is that there is kind of a meta context, and let's denote it with, I don't know, maybe. Let's call it theta. Okay, so we have this. And now we have kind of a dual context. So we have theta, which is the meta context, and after the theta we have the gamma, and this problem lives in this kind of context. and we can refine it even a bit more. So we can kind of split this theta to this. So we have an alpha which has this type. So we have a theta 0, and then we have a theta 1. Okay, let's do this vertical bar, this bar here. So this is the notation which is sometimes used in papers. This is also the notation which I use in the implicit function elaboration paper. So if we have this, and then we have gamma, and then we want to solve this. And now, like we have the usual, like the occurs check. So we have the occurs check, which says that ages cannot depend on alpha. But now, if you think about it, this occurs checking is nothing special, because now I have to do some solution which is valid in theta 0, right? So now this occurs checking is nothing special. This is just part of the strengthening which must be performed. So I just delete this, and here I just say that I have to get a solution for question alpha which lives in theta 0. And in theta 0 there is no alpha, so that's why this solution cannot depend on alpha. So the occurs check just becomes a very special case of the scope checking for the solution. Okay, but it is possible that this array just depends. So possibility array just depends on theta 1, right? Like for example, if I want to solve, maybe I want to solve alpha spine equals beta, but what I have is that this, and then I have beta, and then I have some gamma. Okay, so in this case the problem is that I want to solve alpha, and alpha equals lambda spine dot beta. But now this is not well scoped, so I have to perform a meta strengthening. But this can be already observed in the previous. So in the pruning package, this is already there. So actually the pruning package already is kind of a step away from supporting this kind of glued evaluation, because it already has this top-level scope of metas. So it shouldn't be very hard to extend the pruning implementation with this very simple kind of gluing when so this first version, when meta solutions can refer to meta solutions, but they cannot refer to any other definition. Okay, so and the meta strengthening is that we move metas, move unsolved metas, right? Okay, not necessarily. So we are moving metas back in the meta context. And this is an operation which can fail. So this can fail. And when can it fail? So it can fail if the type of beta does not make sense in the new context. So if the strengthening succeeds, then what we get is just beta, which has type B, but then this B is valid as a closed type, and then alpha, and then this alpha is actually already solved. So this alpha is solved to be lambda spine dot beta, and then, so this is the new meta context after successful strengthening. Okay, and yeah. But the good news is that so this is not. If you know how to implement this, then it's not significantly more complicated if we are doing even the locally scoped methods. So, but let's talk a bit about, so before going to the locally scoped methods, let's talk a bit about what happens if I have the top scoped methods, because there are also some kind of fine details here. And I think so the main question with top scope methods is do we allow solving methods which are in an old block, an old okay, how should I put it? So in general, the elaboration output looks like this. So there is a source def1 dot dot dot, and there is a source def2 dot dot dot, and there is a source def3 dot dot dot, and then there is a meta block 1, meta block 2, meta block 3, right? So there is this interleaving if I have top scope methods. But then the big question, like the big design question, is that can we solve a meta in meta block 1 while we are elaborating, for example, source def2 or 3. So do we allow a meta variable to be solved when we have already moved on? And we can look at Agda. So what happens in Agda? So in Agda, we cannot. So in Agda, we cannot do this kind of solution. But you might ask that, okay, how can this problem even arise in Agda? Because Agda does not use this optimization for meta variables. So Agda does not even have this kind of scoping for meta variables. How is it possible that Agda can rule out like solution of all the meta variables? And the reason is that it's still possible to implement something which is called the meta freezing. And so in Agda, after every top level binding group, the remaining unsolved metas are frozen. And this means that even if there is some potential solution, Agda just doesn't do it. So it cannot be solved anymore. Why does this happen in Agda? So in Agda, the reason that this happens is that Agda has no scoping for meta variables, and in Agda it is possible that I have some like def1, and then I have some data declaration, and then I have some postulate and whatever. And because Agda methods, they don't know about scoping at all, it is possible that I have some meta here, like I have an alpha here, and I have no idea what alpha is, but then I learn what alpha should be, but I only learn it after I have an additional data in the scope. So in Agda, it would be possible to do meta solutions which are completely ill-scoped if we don't have this freezing thing. So Agda use this freezing to rule out just really ill-scoped methods. Ill-scoped meta solutions. but the solution is not really perfect because it is still possible to do kind of a local let block in Agda, and which a local var block in Agda, which also contains postulates or these data declarations, and then actually we can completely easily get ill-scoped metas in Agda, and I think it's just a bug, so it shouldn't be possible to do it. Okay, so but this is Agda, but why would we want to rule out these kind of solutions, right? So why would we want to rule out these kind of solutions? and I think one reason is that we do not want to handle strengthening metas over top level definitions. So we do not want to handle strengthening of metas which crosses over like different meta blocks. So this would be kind of a simplification. We don't want to handle like cross-scope meta strengthening. Okay, so what would be an example for this kind of cross-scope meta strengthening is that maybe I have a I have a def1, and then I have an alpha, and then I have maybe a beta, and then I have a def2. Okay, and let's assume that when I'm elaborating def2, I have no idea about alpha. So alpha is still unsolved, and alpha is not frozen, so I can still solve it. So what happens if in this particular scope, so here I want to solve maybe alpha with beta. And here I still have to perform the strengthening, so I have to move beta back before alpha. So I have to move beta before alpha. But now beta, right? So beta has a type, and the type of beta can depend on this definition, and also so I have to strengthen the type of beta so that it does not depend on this definition anymore. And of course it is possible, but it can be like an extra pain, and we can reason like we don't really care about this kind of cross scope solutions. We just say that if you are writing a top level definition, then you have to make sure that you don't get any unsolved metas after the entire top level definition is elaborated. So we can just say that this is how our elaborator works. And it is also nice if we do this, is that we can already optimize the source definitions after elaborating them. And we don't have to care about metas. So this is another possibility that we're saying that if we have an unsolved meta after elaborating any top level definition, that's an error, right? So we just throw an error that there is an unsolved meta, and then we cannot progress further. And if we do this, then we can already do some optimization passes after each top level definition block, and the optimization pass can just assume that there are no metas anywhere in the elaboration output. Right, and sometimes this makes quite a lot of difference. For example, okay, so this is a bit of an exotic example, but what happens if you want to do like a closure conversion or code generation So what happens if I here have a definition and then I elaborate the definition and I immediately want to generate, for example, a closure converted bytecode or closure converted machine code? Then it makes a lot of difference whether I have to handle unsolved meta variables in this code generation and transformation or not. Like for example, if I have a meta variable inside definition 1, if I have like an all, like a lambda x, y, z, and let's just do like a bunch of local variables here. And in this setup, here I have an unsolved meta, and the unsolved meta is applied to everything in the scope. And if I'm doing a closure conversion, then it's a pretty big loss of space efficiency that every occurrence of this kind of meta variable always drags all of the local variables are dragged into a closure whenever something like this appears. So unsolved metas kind of drag all local vars into closures. Right? Because usually, I mean, in Haskell, when we generate code, then we only have closures which contain just the necessary variables. So if under this particular lambda, I have like let f equals lambda dot a, then this lambda dot a becomes a closure which only has a single capture, right? But if I have a let f equals lambda dot alpha, or maybe like another function applied to this, then here the entire scope is dragged into this closure. So it is a lot more convenient to generate more efficient code if we don't have methods anymore. Okay, yeah. Okay, so I think if we have these top scope methods, then one question is, do we want to freeze methods or not? And there are some reasons why we would do both of these. Okay, I'm not sure that I should start talking about locally scope methods. Maybe it's for another time. I think this is the end of the usual time slot for this seminar. Are any questions or anything which I should speak about specifically? Yeah, so there are lots of details. I only mentioned a few details, so I didn't really prepare like with code or with the agenda here. So I only told the stuff which came into mind, but I'm sure there are a bunch of other details which I'm skipping over or forgetting.
This is not a question, just a technical thing that your sound cuts off a lot of time. It seems to me that it gets more serious as the time passed. So at the beginning it was good, and then worse and worse, and now it's sometimes half sentence is cut off. So
yeah, for me too.
Hopefully the recording will be okay because you did that locally, but because of this I first saw that it's this sensitivity thing, but because it gets worse and worse with time, I think it's maybe something different that we should research what is the cause of this problem, because at the end of the talk it became really bad.
I will first conduct a survey between the listeners to see how many of them this affects, because for me it was pretty good through the whole time.
This is very strange because for me, when it cuts off, then it seems that András, the color of András' name changes. So when András speaks, it's white, and when he doesn't speak, it's gray. And when it's cut off, then it becomes gray. So it seems to like a real problem, but strange that for you.
Yeah, I'm not sure, because if I'm looking at my own screen, then
Okay, it cut off now.
Yeah, so now we didn't hear the second half of the sentence.
Yeah.
I mean, maybe I didn't say the second half of the sentence. Okay, now I also saw that it cut off.
And is your sensitivity on the minimum?
Yes, so there are two possible reasons. One is the sensitivity thing, which you should probably just turn off.
So my input.
But that shouldn't become worse with time.
Okay, let's take this offline. So if there are no more content for the type theory, then I think we can call this over.
Yeah.